So we know that the alternating harmonic series converges, but then the question becomes, well, what does it converge to? Okay, and we can do some checks here, and we can kind of do some estimates of how it converges just with some numbers. So with our numbers, it looked like so far we had it converging to about 0.6628. So what is it getting closer and closer to? Well, it happens that, and again, this is not that we really care what the number it converges to. For our purposes in calculus, we don't really care. We just need to know it converges. But mathematically, it is, if we can figure out what this converges to, it's a good question to answer if we can. So we're going to try to answer this question. What does it converge to? And again, the issue of convergence is much more important to us. But the secondary issue of what does it converge to, well, we're going to look at that right now. So if we take a look at the tables, we can start shading the areas that we have, right? So we had, I think it was, the area that we started with in our table was 1/2, 1/12. Okay, so we're going to shade 1/2. So I take this area here. Actually, I'm going to use a highlighter here. I'm going to shade 1/2. Okay, so I'm going to take that area and shade that all in. Okay, so that was the first sum. Okay, 1/12. Okay, that's about 88.83 of 100. So that's going to be about 8 of these, a little bit more. Okay, and then 1/30 is going to be a little bit more than 3. Okay, 3 of these, and then 1/56, that's about 2. Okay, then it's going to be 1/90, a little bit more than 1. 1/132, so it's just about, just a little bit less than 1. 1/240, I think it was. What was the next one? 1/182, so it's going to be about half of a square. Okay, so then 1/240, about another half square, and we're starting to get a limit here. So if I count this up, this is going to be about 60, 1, 2, 3, 4, 5, 6. Let's say 0.67, and it's just going to keep on growing and growing a little bit more, a little bit more. So it's looking to be closer and closer to, yeah, this number seems reasonable. Okay, so we can kind of see that it's tending towards a number. It's a bit of a stretch to say it's 0.69, but it is at least in the neighborhood of 0.69. We could do the same thing here. We can do a number line check. We can just start doing, we have 1. We're going to subtract a half. We're going to add a third. Okay, we're going to subtract a quarter. So it's going to look kind of like that. A quarter is maybe about that long. Okay, we're going to subtract or add an eighth, or so add 1/5. So 1/5 maybe about that long. And you can see that if the way that we're drawing this is definitely bounded, because there's no way every term is smaller. And if we're reversing direction, each time we reverse direction, this tip is never going to go past the last tail. So this tip doesn't go past the last tail. This tip won't ever go past that tail. This tip won't ever go past that tail. So we start going back and forth and back and forth. And in fact, that back and forth seems to be, okay, so it's going to go like this, like this, like this, like this, like this, like this, and it's going to tend towards the value somewhere around there. And, looking at that on the number line, yeah, that's not completely unreasonable to say that's approximately 0.69. So again, on the number line, we can kind of justify, yeah, it's just going to go back and forth between there. Here we're taking, the partial sums, like grouping them, but here we're just taking the individual ones. And we can see that they never go past the last tail. So it has to converge to some point. And that point physically is somewhere around there. Okay, and that point, we're kind of leaning towards and arguing that maybe this is 0.69.